In 2019, the estimate was 20 million qubits. That number came from a specific paper by a specific researcher working through a specific problem. How many physical qubits would a fault-tolerant quantum computer need to break RSA 2048, the encryption standard protecting most of the world's banking, email, and digital certificates? The answer was 20 million. That number entered the literature. It entered government planning documents. It entered corporate risk assessments. It became the foundation on which an entire industry told itself it had time. In May 2025, the same researcher published again. The new estimate was under 1 million physical qubits, a reduction of more than 95%. Not a competing paper from a rival team, not a fringe claim from a startup chasing investment. The same researcher, revising his own work, downward, by nearly the full amount. That is the number this is about. Not because it proves anything has been broken yet, because of what it means that the number moved that far, that fast, from that source. Here is what most quantum computing coverage gets wrong. It treats every new announcement as an isolated event, a new chip, a new qubit record, a new benchmark on some abstract computation. The story gets written, the headline fades, and nothing changes for most people because nothing has visibly changed. The threat is always described as years away. The timelines are always described as uncertain, and after enough cycles of that pattern, the announcements stop registering as signal. They read as noise. This is not that. What happened between 2019 and 2025 is not another chip announcement. It is the collapse of the numerical buffer that separated quantum computing theory from quantum computing threat. The 20 million qubit estimate was not just a technical benchmark, it was a timeline. It said, the engineering challenge is so large that by the time it is solved, organizations will have had decades to migrate their cryptographic systems. 20 million qubits implied safety through scale. The problem was so big that the solution was necessarily far away. Under 1 million qubits changes that calculation entirely. It does not just move the threat closer, it moves the threat into a range where current engineering progress becomes directly relevant, where machines being built today are measurable fractions of the required scale rather than rounding errors against it. The researcher who published the original estimate is Craig Gidney at Google. In 2019, Gidney and his co-author Martin Ekero worked through the precise quantum resources required to factor a 2048-bit RSA key. Their result was 20 million physical qubits, operating for approximately 8 hours. That paper became the canonical reference. When government agencies wrote planning documents about the quantum threat timeline, they used that number. When technology companies estimated how long they had before migration became urgent, they used that number. When security professionals briefed executives on quantum risk, the slide deck cited that number. What Gidney found in 2025 were algorithmic improvements, better methods for performing the underlying mathematical operations, more efficient use of quantum gate sequences, the kind of progress that does not require better hardware at all, only a better understanding of how to use the hardware that will exist. The physical qubit requirement dropped below 1 million. The 8-hour factoring window remained roughly intact. The 95% reduction in scale came entirely from thinking more carefully about the algorithm. Here is why that matters in a way that goes beyond the specific numbers. Every threat model, every timeline, every planning document that used 20 million as its foundation was built on the assumption that algorithmic efficiency had already been pushed close to its limits, that the hard engineering challenge of building tens of millions of qubits was the primary remaining barrier. Gidney's 2025 paper did not just revise a number. It revealed that the barrier was significantly smaller than the field had believed, and that the revision came from a source with no incentive to minimize the problem. The stakes here are not abstract. Every encrypted connection on the internet relies on a mathematical asymmetry. Certain operations are easy to perform and nearly impossible to reverse without specific information. Public key cryptography is built entirely on that asymmetry holding. RSA, elliptic curve encryption, the systems underneath HTTPS, digital signatures, financial transactions, government communications. The entire architecture of digital trust runs on the assumption that certain mathematical problems are computationally hard. Shor's algorithm, which has been known since 1994, breaks that assumption for a sufficiently powerful quantum computer. The question has always been what sufficiently powerful means in practice. For 6 years, the answer was 20 million qubits. That was the number. It implied a timeline comfortable enough that the problem could be managed through normal institutional processes, planned migrations, gradual adoption of post-quantum cryptography standards. It was a hard problem with a long horizon. The horizon just moved. What makes this particular moment different from 30 years of quantum computing announcements is exactly that quality of wrongness that appears when a number in the published literature stops being explainable at its face value. The estimate did not drift. It did not adjust incrementally through competing papers arguing at the margins. It dropped by 95% in a single publication from the person who produced the original. That pattern does not appear in normal scientific progress. It appears when a foundational assumption was incorrect. And when a foundational assumption in a field is incorrect, the correct response is not to note the revision and continue with adjusted timelines. The correct response is to ask how the assumption survived as long as it did. And the man who published ed 20 million was the same man who published the correction. Every time you send a bank transfer, something mathematical happens that is worth understanding because it is the exact thing that is now at risk. Here is the thing about public key cryptography that nobody explains up front. It is not a complicated idea. The complication is in what it protects and how completely it protects it and what happens when the protection fails. Start with the basic structure because the basic structure is the whole argument. Think of it like a padlock, an open padlock. Anyone can snap it shut. That part is easy, but only the person with the key can open it again. What RSA does is a mathematical version of this, where the padlock is a number so large that factoring it back into its original components is, for all practical purposes, impossible. Your browser generates a public key, which is the open padlock, and a private key, which is the only thing that can open it. The public key gets shared freely. Anyone can use it to lock information intended for you. But only your private key, which never leaves your machine, can unlock it. The asymmetry is the point. Easy to lock. Effectively impossible to unlock without the key. That asymmetry is the entire foundation of digital trust, not part of it, all of it. When you visit a website over HTTPS, your browser and the server perform a handshake. They establish a shared secret using exactly this mechanism. The green padlock in your browser's address bar is telling you that the connection is secured by this asymmetry, that someone without the private key cannot read what passes between you and that server. Every bank transfer, every login, every piece of sensitive data moving across any network on Earth is protected by some version of this mathematical property, not by firewalls, not by passwords, by the fact that certain mathematical operations are easy in one direction and computationally ruinous in the other. Digital signatures work the same way in reverse. When a software company signs a piece of code before releasing it, they are using their private key to generate a signature that anyone can verify using the corresponding public key. Your device checks that signature every time it installs an update. The signature proves the code came from who it claims to come from and has not been modified in transit. Strip that verification out, and there is no reliable way to know whether the software running on your device was built by the company whose name is on it or by someone who intercepted it on the way to you. Email encryption runs on the same mathematics. So does the infrastructure that authenticates servers to each other. The certificates that tell your browser a website is what it claims to be. The systems that verify the identity of devices connecting to corporate networks. This is not a list of separate technologies that each happen to use similar math. It is one mathematical assumption, instantiated across thousands of different systems, holding all of them up simultaneously. The specific hardness problem underlying RSA is integer factorization. Take two large prime numbers, multiply them together, and you get a product that is trivially easy to compute but, given only the product, essentially impossible to factor back into its original components with any classical computer. The numbers involved are not large in the everyday sense. They are hundreds of digits long. The fastest classical algorithms known cannot factor a 2048-bit RSA key in any useful time frame. When researchers estimate how long it would take, the answers come back in years that exceed the age of the universe. That is not a figure of speech. That is the actual computation. Here is what that means in practice. When a government agency, or a bank, or a technology company says your data is encrypted with RSA 2048, They are saying that even an adversary with access to the most powerful classical computers ever built cannot break that encryption before the sun expands to consume the Earth. The security is not conditional on keeping secrets about the algorithm. The algorithm is published. The security comes entirely from the hardness of the underlying mathematical problem. That is an extraordinary thing to build the entire digital economy on top of. And it has worked for decades because no one had a fast way to factor large numbers. The assumption sitting underneath all of it, the one assumption every bank and government and technology company has built on, is that factoring is hard, that it will stay hard, that no one will find a shortcut. Peter Shor found the shortcut in 1994. He published a quantum algorithm that factors large numbers efficiently, in a way that grows polynomially rather than exponentially with the size of the number. Not faster in a meaningful but incremental way. Faster in a way that transforms centuries of computation into hours. The mathematical hardness that RSA depends on does not exist for a machine running Shor's algorithm. The asymmetry disappears. The padlock becomes transparent. Shor's algorithm does not pick the lock. Peter Shor published the algorithm in 1994, and the field has spent 30 years figuring out how to actually run it. Here is what the algorithm does. RSA encryption is protected by a mathematical problem. Take two very large prime numbers and multiply them together. That product is public. The primes are private. Anyone who wants to break the encryption needs to factor the product back into its two original primes. On a classical computer, that takes an amount of time that scales so badly with the size of the number that breaking a modern RSA key would require longer than the age of the universe. That is the trapdoor. Factoring is easy to describe and practically impossible to do. Shor's algorithm changes the cost of that problem entirely. On a quantum computer, factoring does not scale the same way. What takes a classical computer billions of years takes a quantum computer hours. The mathematical lock that protects every encrypted system on Earth assumes classical hardware. Shor's algorithm is the moment that assumption stops being safe. So why is this still a problem in 2025 and not a solved problem from 1994? Because running Shor's algorithm requires a quantum computer that does not make mistakes, and quantum computers make mistakes constantly. This is the core issue. A qubit, the basic unit of quantum computation, is extraordinarily sensitive to its environment. Heat, vibration, stray electromagnetic fields, proximity to other qubits. Any interference at all disrupts the quantum state and introduces an error. Classical computers have errors too, but classical bits are either 0 or 1. They are robust. A qubit exists in a quantum superposition, holding multiple states simultaneously, and the slightest disturbance collapses that superposition in the wrong direction. The computation fails. You get a wrong answer. The solution is quantum error correction. You encode one logical qubit, the qubit doing the actual computation, using many physical qubits, the ones you actually build in hardware. The physical qubits monitor each other. When one drifts, the others catch it and correct it. The logical qubit stays stable. The problem is how many physical qubits it takes to protect one logical qubit reliably. Early estimates suggested somewhere between 100 and 1,000 physical qubits per logical qubit, depending on the error rate of the hardware. And Shor's algorithm requires thousands of logical qubits to factor the key sizes used in real RSA encryption. Do the multiplication. Thousands of logical qubits times hundreds to thousands of physical qubits each equals millions of physical qubits in total. That is not the end of the problem. It is where the problem compounds. More physical qubits mean more sources of error. More sources of error mean more error correction overhead. More overhead means more physical qubits. The system grows faster than the capability grows. Every qubit you add to improve reliability also adds new failure points that need their own correction. There is a threshold somewhere in that dynamic. Below a certain error rate per physical qubit, the error correction works, and the system gets more reliable as it scales. Above that threshold, it does not matter how many qubits you add. You are just adding more noise. For most of the 3 decades since Shor published, the hardware was above that threshold, nowhere close to below it, which meant fault-tolerant quantum computation, the kind needed to actually run Shor on a real key, was not physically achievable. The algorithm existed. The hardware did not. In 2019, researchers Craig Gidney and Martin Eckerow put a number on what it would take. Their analysis was careful, specific. They modeled running Shor's algorithm against RSA-2048, the standard that protects most banking, most email, most digital certificates on the internet. Their conclusion was that a fault-tolerant quantum computer would need approximately 20 million physical qubits and roughly 8 hours of sustained computation. Not 20 million qubits with current error rates. 20 million qubits operating below the error correction threshold, with the overhead accounted for, with the logical qubits properly encoded and maintained throughout the full runtime of the algorithm. That number became the canonical benchmark. Every government planning document, every corporate risk assessment, every academic threat model absorbed it. And the implication was comfortable. The most advanced quantum hardware at the time had hundreds of qubits. Even optimistic projections for scaling quantum computers suggested that reaching 20 million reliable physical qubits was decades away. The NIST post-quantum migration guidance was built around a 2035 timeline partly because of that number. The corporate security teams that reviewed quantum risk and decided to monitor the situation rather than act were doing the rational thing given that number. 20 million qubits meant the threat was real in theory and irrelevant in practice, which is a very comfortable place to stop thinking about something. December 2024 is when the theoretical stopped being theoretical. For 30 years, the argument against taking Shor's algorithms seriously as a near-term threat came down to one word: noise. Quantum hardware is unstable. Qubits collapse. They pick up interference from temperature fluctuations, from electromagnetic fields, from the act of measurement itself. Every operation you run on a quantum computer introduces errors, and the more qubits you add, the more errors you get. This was the practical wall that stood between a 1994 algorithm and any real-world consequence. The theory was there, the hardware was not. And for most of those 30 years, there was no compelling reason to think the hardware would get there on any schedule that mattered. Here is the thing about quantum error correction that the coverage of the Willow chip mostly missed. The threshold is not a goal, it is a phase transition. Below a certain error rate per qubit, something changes in the mathematics of the system. Adding more qubits no longer makes the problem worse, it makes it better, exponentially better. Each additional qubit contributes more to correcting errors than it contributes to creating them. The system becomes self-stabilizing. Above that threshold, the opposite is true. Adding qubits adds noise faster than correction can absorb it. The system falls apart as it scales. This means there are effectively two different regimes of quantum computing separated by a single error rate. One regime is a dead end. The other is the foundation for fault-tolerant quantum computers capable of running Shor's algorithm at the scale the resource estimates require. For 3 decades, the skeptics' position rested entirely on one claim: that real quantum hardware you could actually build and operate, would always live above that threshold. The noise floor of physical qubits would always be too high. You could push it down, but you could not push it down enough. This was not an unreasonable position. Every attempt to build larger quantum systems seemed to confirm it. Error rates improved slowly. The threshold remained out of reach. And because the 20 million qubit estimate for breaking RSA-2048 assumed error correction that required crossing that threshold, the skeptics had a clean logical argument. The resource estimates assume error correction. Error correction requires crossing the threshold. We cannot cross the threshold. Therefore, the resource estimates are unreachable. Full stop. Google's Willow chip crossed the threshold. What the December 2024 result demonstrated is worth stating precisely. Willow did not break encryption. It did not factor a large number. It did not run Shor's algorithm. What it demonstrated is that when you add more qubits to the Willow architecture, the logical error rate goes down instead of up. They tested this across multiple code distances, meaning multiple configurations of physical qubits working together to protect a single logical qubit. And as the code distance increased, as they added more physical qubits to the system, the error rate fell exponentially, not linearly, exponentially. That is the threshold behavior. That is the phase transition. That is the thing that was supposed to be physically unachievable. The reason this matters beyond the headline is structural. Every estimate of what it would take to build a quantum computer capable of breaking RSA had error correction built into its assumptions. Those assumptions required crossing the error correction threshold. Anyone running resource estimates before December 2024 was doing so with a theoretical asterisk attached. The threshold was predicted to exist by quantum error correction theory, but it had never been demonstrated in a physical system. Skeptics could always point at that gap. The models say it should work, but models are not chips. Real hardware has properties that models do not capture. Maybe the noise floor has some physical lower bound we have not found yet. Maybe the threshold behavior does not persist as systems scale up. These were legitimate questions, not fringe objections. They were the kind of questions that serious researchers raise about untested physical assumptions. Willow closed that argument, not partially, not tentatively. The threshold is real. It is physically achievable. The behavior the theory predicted is the behavior the hardware produced. What remains between Willow and a cryptographically relevant quantum computer is substantial. Willow operates with 105 physical qubits. Breaking RSA-2048 under even the most optimistic post-Gidney estimates requires hundreds of thousands of physical qubits sustaining fault-tolerant computation across minutes or days. The engineering distance between 105 qubits and several hundred thousand is not trivial. Fabricating chips at that scale, managing the classical computing infrastructure required to process syndrome data in real time, maintaining coherence across that many qubits long enough to complete the computation, none of these problems are solved. They are hard problems. Some of them may turn out to be harder than they currently appear. But here is what changed in December 2024. Every one of those remaining problems is an engineering problem, not a physics problem. Before Willow, skeptics had a physics argument. The hardware cannot get there because the noise floor cannot go low enough. That argument required no engineering solution because it claimed the underlying physics would not cooperate. Willow eliminated it. The noise floor can go low enough. The error correction behavior the theory predicted actually appears in physical hardware at the rate the theory requires. The remaining barriers are about scale, fabrication, and systems engineering. Those are genuinely difficult. But the history of engineering is the history of solving genuinely difficult problems when the underlying physics cooperates. The physics works. 6 years after publishing the estimate that the entire industry used to tell itself it had time, Craig Gidney published again. The 2019 number was 20 million physical qubits. That was the resource requirement to factor a 2048-bit RSA key in approximately 8 hours using a fault-tolerant quantum computer. Gidney and his co-author Martin Eckero derived it carefully. It became the canonical benchmark. Governments cited it. Corporate security teams built migration timelines around it. Risk assessments across the financial sector, the defense industry, and critical infrastructure planning all anchored to that number. 20 million qubits meant you had time. Current hardware sits in the hundreds to low thousands. The gap was comfortable enough that you could acknowledge the threat, note it in the documentation, and keep doing other things. The May 2025 paper changed the number to under 1 million. That is not a refinement. 95% of the original estimate, gone. The same researcher, the same problem, a different answer by an order of magnitude. And here is what that actually means for every planning document that used the 2019 figure as its foundation. It means the foundation was wrong. Not because Gidney made a mistake in 2019. He did not. He worked from the best available understanding of how fault-tolerant quantum computation would have to be structured. What changed in 2025 was the understanding itself. Here is my position on the credibility question, because it matters enormously. When a startup publishes a paper claiming it can break RSA with far fewer resources than established estimates, the rational response is skepticism. Startups need to raise money. Dramatic claims serve that purpose. You weight the claim accordingly and wait for independent verification. Craig Gidney is not a startup. He is one of the most respected researchers in quantum error correction. He is employed at Google, the institution that produced the Willow chip result described in the previous section. And critically, he is the author of the 2019 estimate he is now revising downward. He is not attacking someone else's number. He is correcting his own. That distinction is worth sitting with. What changed algorithmically involves improvements in how quantum circuits handle the specific mathematical operations needed to factor large numbers. The rough version is this. The original estimate assumed a particular approach to modular exponentiation, which is the core computation in Shor's algorithm. That approach was reasonable given what was known in 2019. Subsequent work, including Gidney's own intervening research, found more efficient methods for implementing the same operations using fewer quantum gates. Fewer gates means fewer opportunities for errors to accumulate. Fewer accumulated errors means fewer physical qubits needed to maintain the required error correction threshold. Each improvement compresses the resource requirement further. The result is not that Shor's algorithm changed. It did not. The result is that the engineering pathway to running it became dramatically more efficient than anyone had modeled. And the new pathway puts the qubit requirement inside a range that serious hardware roadmaps now treat as achievable this decade. Now look at what that does to the institutional landscape. Every risk assessment that used 20 million as its anchor was calibrated to a threat that felt distant. 20 million physical qubits implied a quantum computer vastly larger than anything on any current hardware roadmap. The threat was real, acknowledged, serious in principle, and comfortably far away in practice. That comfort was not irrational. It was built on the best published science available at the time. But the moment the estimate drops below 1 million, it crosses a threshold that changes the character of the problem entirely. Current hardware roadmaps include targets in the low millions, not in 50 years. In this decade, the gap between where the hardware is going and where the threat begins to become relevant just collapsed from an enormous comfortable distance to something that fits inside a single corporate planning cycle. Why did nobody close this gap before 2025? That is the honest question, and the honest answer is that the algorithmic improvements required insight that simply was not available earlier. This is not a case of institutional reluctance to look at uncomfortable data. The efficiency gains Gidney found in 2025 were not obvious. They required detailed understanding of how specific quantum circuit components interact with error correction requirements. The field was working on these problems throughout the 6-year gap. The result just arrived later than anyone would have preferred. Here is the dark part. The result arriving later than preferred is not the same as arriving with enough time to respond. Every corporate security team that treated the 2019 number as a planning anchor now has a gap between their migration timeline and the revised threat window. Every government agency that built its quantum preparedness schedule around 2 decades of runway is recalculating. Every risk model that fed into insurance underwriting, infrastructure investment decisions, and classified threat assessments has to absorb a number that is 95% smaller than the one it was built on. That is not an adjustment. That is a reconstruction. The organizations that started early, the ones that began inventorying cryptographic dependencies and piloting post-quantum standards before anyone required them to, those organizations absorbed this revision as a timeline acceleration. Difficult, but manageable. The organizations that were waiting for the threat to get closer before committing resources found out that the threat got closer faster than the model said it could. And the man who told them it was far away is the same man who told them it is not. There is a specific kind of institutional weight that comes from a researcher revising their own benchmark. It removes every argument that this is motivated reasoning from an outside critic. It removes the possibility of dismissing the new number as coming from someone who does not understand the original methodology. Gidney understood it, he wrote it, and 6 years later, with better tools and better insight, he looked at it again and found it wrong by an order of magnitude. The benchmark that gave the world 20 years of breathing room was gone in a single paper. What makes this different from every previous quantum computing announcement is not one paper. One paper can be wrong. One paper can reflect a single team's assumptions, a single methodology, a single set of optimistic conditions that don't generalize. The history of quantum computing is full of results that generated headlines and then quietly failed to replicate or scale. That is the normal pattern. What happened between May 2025 and early 2026 is not the normal pattern. 3 independent teams, different countries, different institutions, different mathematical approaches to the same underlying problem. All of them arrived at essentially the same conclusion. The qubit requirements to break RSA-2048 are dramatically lower than the field believed. Not slightly lower, not lower in a way that adjusts timelines by a few years. Lower in a way that moves the threat from a distant planning problem into a near-term engineering problem. When you see one line of evidence pointing at an uncomfortable conclusion, you can explain it away. When you see 3 from researchers who were not coordinating with each other, the explanation gets harder to construct. The second paper came from a team at the University of Rennes working with INRIA, CNRS, and IRISA. The researchers are Chevignard, Fouque, and Schrottenloher. Their approach was technically distinct from Gidney's. Where Gidney focused on algorithmic improvements to the overall factoring process, the Rennes team concentrated on something more specific: approximate modular arithmetic. The idea is that breaking RSA does not require perfect computation at every step. If you can tolerate some approximation in certain parts of the calculation, you can use far fewer logical qubits to perform the operations that matter. Their analysis pushed the logical qubit requirement for RSA 2048 down toward roughly 1730, a number so low it would have seemed implausible as a serious estimate 2 years earlier. The trade-off is gate count. Fewer qubits means more operations, and their approach requires trillions of Toffoli gates to compensate. That is a real cost. But here is what the Rennes result demonstrates regardless of where you come down on the trade-off. There is more than one path to breaking this encryption. Different assumptions, different architectures, different mathematical entry points, and they all lead to the same destination. That matters. What it tells you is that this is not a single fragile theoretical attack that depends on one specific set of conditions holding. The vulnerability has depth. Multiple independent approaches reach it. That is a different kind of threat than one clever algorithm that might or might not pan out in hardware. The third paper is the one the field has been most careful about discussing openly. A team including researchers who had previously worked at Google published through a company called Oratomic. The paper incorporated artificial intelligence into the process of finding more efficient quantum attack algorithms, and the authors made deliberate choices about what to publish. They held back portions of their methodology. They withheld details about how AI had been used in deriving key results, with plans to publish that in a follow-up paper. One researcher involved, who had left Google Quantum AI before co-founding Oratomic, told a contact still inside Google's quantum initiative that he had been using AI and was seeing, in his words, lots of crazy results. Sit with what that means. A team is using artificial intelligence to search for more efficient ways to break encryption, and they are finding things they consider too sensitive to publish in full. That is not a theoretical concern about some future intersection of AI and quantum computing. That is a present-day event. The AI is not breaking encryption. The AI is helping researchers find quantum algorithms that could break encryption more efficiently than humans had previously conceived. The search space for cryptanalytic algorithms is enormous. Humans exploring it manually will miss things. AI exploring it will not miss the same things. What the Oratomic result suggests is that the compression of qubit requirements we have already seen may not be the flaw. Gidney himself has said that under his current model, he does not see another tenfold reduction without a fundamental change in assumptions. That is probably right for the approaches he has been working on. The question the Oratomic result raises is whether AI-assisted search finds approaches he has not been working on. Here is my position on the institutional response to all three of these papers. It has been careful. It has been professional. It has been almost entirely inadequate to the speed of what is happening. When Gidney published his revision, the field acknowledged it. When the Rennes paper appeared, it was discussed and noted. When the Oratomic results circulated, Google moved its own internal migration deadline to 2029. That is an acknowledgement. But acknowledgement and response are different things. The same gap that Frank and Schmidt identified about the PETM, a result published, covered, and then allowed to sit unanswered for years, is visible here in a different form. The papers are being read. The conclusions are being accepted. The urgency implied by those conclusions has not translated into action at the scale the conclusions require. 3 independent groups, different methods, different institutions, all arriving at the same conclusion within 12 months. And the institutional response has been to note the findings carefully and continue the migration planning that was already underway. The most dangerous aspect of the current situation is not 4 years away. That framing matters. Almost every public discussion of the quantum threat is structured around a future event. Q-Day arrives, quantum computers cross some capability threshold, and then the encryption breaks. That sequence implies a gap between now and the problem. It implies time. Here is what that framing gets wrong. The attack does not begin when the quantum computer exists. The attack begins when someone decides to save the data. Store now, decrypt later. The concept is straightforward and the implications are not. An adversary, a state intelligence agency, a well-resourced criminal organization, any actor with the infrastructure to intercept and store encrypted traffic at scale, does not need a quantum computer today. They need a storage system and patience. They collect encrypted communications now. They hold them. When quantum computers reach cryptographic relevance, they decrypt. What was secure in 2026 becomes readable in 2030. The breach happened in 2026. The damage lands in 2030. And the organization whose data was taken has no way to know which conversation, which file transfer, which authentication exchange is sitting in someone else's archive right now. This is not a hypothetical attack. It is an operational posture that any serious intelligence apparatus would adopt the moment they understood the quantum timeline. And the quantum timeline has been publicly documented for years. Think about what gets encrypted, not just passwords, drug formulations under active patent, merger negotiations before public announcement, military logistics, diplomatic backchannels, intelligence source identities. The value of that information does not expire when the encryption is broken. A drug compound designed in 2026 and patented in 2028 is still worth stealing in 2030, even if the encrypted research files were collected 4 years earlier. A source identity revealed in 2030 from a 2026 intercept is still a person at risk. Government communications about infrastructure vulnerabilities do not become harmless because time passed between collection and decryption. The entire category of information that was worth encrypting in the first place is largely the same category worth decrypting years later. Here is what that means for the migration deadline. The standard framing treats post-quantum cryptography as a preparation for a future threat. Migrate before Q-Day and you are protected. Migrate after Q-Day and you are exposed. That calculus assumes the threat clock starts when quantum computers arrive. It does not. For any data that is currently being collected and stored by a state-level actor, the exposure clock started the moment that collection began. Migrating to post-quantum cryptography in 2028 does not protect communications that were intercepted in 2024. It protects communications from 2028 forward. Everything before that date remains in archives that quantum computers will eventually be able to open. The sensitive question is what has already been collected. No one outside the relevant intelligence agencies knows the answer. What we do know is that the architecture for collecting and storing encrypted internet traffic at scale exists. It has existed for decades. The Snowden documents from 2013 confirmed that programs designed for exactly this kind of bulk collection were operational. That was before the quantum threat timeline compressed, before Willow, before Gidney's revision, before 3 independent research teams reduced the qubit requirements by an order of magnitude in 12 months. What would a rational state actor do with that collection infrastructure after reading the last 5 years of quantum computing research? The answer is not complicated. There is a particular category of information where this becomes acute. Communications that governments and militaries intend to remain classified for decades. The standard classification cycle in most Western governments runs 10 to 30 years for sensitive material. Documents classified in 2026 with a 30-year protection window are expected to remain secret until 2056. That window was designed around the assumption that current encryption holds. It does not account for the possibility that an adversary is archiving those communications today with a quantum computer in mind for 2030. The 30-year window and the 4-year Q-Day estimate do not fit together cleanly, and the delayed breach concept cuts in a direction that most breach discussions do not. When a company gets hacked in the conventional sense, there is typically a detection event. Logs show anomalous access. Data volumes move in unexpected ways. Forensic investigators can identify what was taken and when. A harvest-now-decrypt-later attack leaves none of that. The interception happens at the network level. No system inside the organization is touched. There is no alert, no anomaly, no indication that anything occurred. The organization continues operating normally while its encrypted traffic accumulates in someone else's archive. The first sign of the breach is not the collection. It is the consequence, years later, when the decryption produces usable intelligence. That structure makes retrospective protection essentially impossible. You cannot go back and re-encrypt data that was already intercepted. You cannot undo communications that were already captured. The only protection is forward-looking, which means the only data that can still be protected is data that has not yet been transmitted. The window for protecting data that needs to stay secret for the next decade closed the moment any state-level actor decided to start collecting. When cryptographers say PKI collapses, they are not describing an incremental failure. They are describing something specific, something structural, the kind of failure that does not announce itself with a single breach notification and a press release. It is worth being precise about what public key infrastructure actually is before explaining what breaking it means, because the word infrastructure does most of the work here and almost nobody stops to think about what it is holding up. Every time your browser shows a padlock, something is happening in the background. A certificate is being verified. That certificate was signed by an authority whose identity is itself verified by another certificate, which traces back to a root certificate that your operating system was shipped with and trusts automatically. This chain is how your browser knows that the website you are connecting to is actually that website and not someone else pretending. The entire chain depends on RSA or elliptic curve cryptography. Every link, every signature, every verification at every level. The mathematical hardness of factoring large numbers is what makes the chain hold. Take that away, and the chain does not weaken, it becomes meaningless. Here is what that looks like in practice. HTTPS, the protocol that encrypts the majority of web traffic on Earth, relies on this chain for both encryption and authentication. When you enter a password on a login page, the encryption protecting that password in transit depends on a key exchange process that Shor's algorithm can break. When your bank's website proves to your browser that it is your bank and not an impersonator, that proof rests on a digital certificate signed with RSA. When software updates arrive on your phone or your laptop, the signature that tells the operating system the update is legitimate and has not been tampered with uses the same mathematics. None of these are separate systems with separate vulnerabilities. They are one system, and the vulnerability is in the foundation. Bas Westerban, a researcher at Cloudflare who works directly on post-quantum cryptography deployment, put it plainly. Almost every system in the world becomes vulnerable altogether to a quantum attacker. That word altogether is the one that matters. This is not a scenario where attackers compromise one bank, then another bank, then a hospital, then a government system, sequentially, one at a time, with defenders getting time to respond between incidents. The vulnerability is simultaneous. The moment a quantum computer capable of running Shor's algorithm at the required scale exists, every system that has not already migrated to post-quantum cryptography is exposed at the same instant. Think about what is on that list. Every major financial institution's encrypted communications, every government agency's authenticated network traffic, every digital certificate that signs the software running on every device connected to the internet, every secure email protocol, every VPN connection protecting corporate networks, every authentication system that relies on asymmetric keys. The attack surface is not large, it is total. Normal cybersecurity threats do not work this way. A vulnerability in one piece of software affects the systems running that software. A zero-day exploit against a specific protocol affects systems using that protocol. Defenders can isolate, patch, and contain. The asymmetry of defense and offense is unfavorable but manageable. What a cryptographically relevant quantum computer creates is categorically different. There is no patch for RSA once Shor's algorithm is running at scale. The mathematical property that RSA relies on, the difficulty of factoring the product of two large primes, does not get harder to break if you update your software. The vulnerability is in the algorithm. The algorithm is in everything. And here is the part that does not get said clearly enough. The cascading failure does not require an attacker to target every system individually. It requires one thing: the existence of a machine capable of running the attack. After that, the question of which systems are compromised is a question of attacker priorities and available time. Governments, financial infrastructure, critical systems first. Everything else in whatever order seems useful. The defenders are not responding to individual incidents. They are responding to the collapse of the property that made defense coherent in the first place. What does that actually look like? Software updates that can no longer be trusted as legitimate. Digital certificates that can no longer be verified as genuine. encrypted communications that are indistinguishable from communications that have already been read, authentication systems that cannot confirm identity. The lock on every door is the same lock and the same key opens all of them. This is why the response from Cloudflare, Apple, and Google has not been incremental security hardening. It has been full migration to new cryptographic foundations. Not because the current systems are old, because the current systems rest on an assumption about mathematical difficulty that a quantum computer removes entirely. Once that assumption is gone, it is not gone for one system. It is gone for all of them. Not a breach, not a hack. A simultaneous loss of the mathematical property that makes digital trust possible at all. The year that keeps appearing in serious planning documents is 2030, not 2040, not 2050, 2030. Forrester published it. Google Quantum AI published it. Government threat assessments reference it. And if you look at where expert consensus on this question sat 5 years ago versus where it sits right now, the shift is not incremental. It is a different conversation entirely. A 2025 survey of experts in the field found that between 28 and 49% of respondents considered a cryptographically relevant quantum computer quite possible within 10 years. Between 51 and 70% considered it likely within 15. Those numbers sound measured until you understand what they represent. This is not a fringe position. These are the people who build and study the hardware. And they moved. The older estimates placed Q-Day comfortably beyond the horizon. Not in your career, not in the planning cycle, somewhere in the abstract future where budgets do not reach and urgency does not live. That comfort was built on the 20 million qubit benchmark. That benchmark is gone. What replaced it is a set of estimates that compress the timeline into a range your current infrastructure will still be running inside. When you ask why the expert consensus shifted so sharply and so quickly, the answer is not one paper. It is the pattern the papers reveal together. The assumptions that held the long timeline in place fell, one after another, inside a 12-month window. Here is what the engineering obstacles actually look like at this point. They are real. Sustaining fault-tolerant computation across hundreds of thousands of qubits for the duration required to factor a 2048-bit RSA key is not solved. Real-time syndrome decoding, the classical processing that reads every error signal from every qubit and feeds corrections back fast enough to matter, generates terabytes of data. Current classical hardware is not built to process that throughput at scale. QLDPC code architectures, which would reduce qubit requirements further, require qubit connectivity that does not yet exist in manufacturable form. These are not trivial obstacles. Here is my position on what they mean for the timeline, though. They are engineering problems, not physics problems. And there is a difference. Physics problems can stop a field entirely. Engineering problems get solved incrementally, with money and time and focused effort. The theoretical framework is now confirmed. The error correction threshold is physically achievable. What remains is systems work. That is a different category of challenge than the one the field was facing in 2019, and the timelines being published now reflect that distinction. When Gidney revised his estimate from 20 million qubits to under 1 million, the remaining obstacles shifted. Fewer qubits means less syndrome data. Less syndrome data means less processing load. Each algorithmic improvement reconfigures what the engineering problem actually is. There is no obvious flaw in sight yet. That matters. What does that tell you about the 2030 estimate? It tells you it is a probability, not a certainty. No serious researcher is claiming the date is fixed. What they are claiming is that the range has narrowed enough that organizations treating this as a distant future problem are already operating on outdated assumptions. The survey range of 28 to 49% within 10 years is not a prediction of inevitability. It is a professional community telling you that the coin is in the air and the odds are no longer negligible. That is a different posture than the field held even 3 years ago, and the posture change happened because the data changed, not because researchers became more alarmist. Why is that not the framing every corporate planning document opens with? The absence that matters here is not institutional silence. There has been response. NIST published standards, agencies issued mandates, governments designated years. But acknowledgement and adjustment are different things. The organizations building planning documents around 2030 are the organizations that started revising their assumptions the moment the data moved. For every Forrester report citing 2030, there are enterprises that have not yet inventoried the RSA implementations inside their own infrastructure. For every agency updating its threat model, there are supply chains, hospitals, financial institutions, and critical systems operating on a timeline that has not been revised since Gidney's 2019 number was the canonical reference. The gap between the institutions that are tracking this closely and the institutions that are not is where the actual risk lives. Here is the thing about Google moving its internal deadline to 2029. Google operates the most advanced quantum computing program in the world. Google has Willow, Google has Gidney. When Google announces publicly that it will migrate its own systems to post-quantum cryptography 6 years before NIST's official 2035 guidance, that announcement is carrying information, not speculation, information. The company with the deepest view into the current state of quantum hardware looked at what they were building and decided the official timeline was not the one to use. That is not a bureaucratic judgment. It is a technical one made by people watching the hardware from the inside. You can ask what they know. You can also just look at what they did. Google set its internal deadline at 2029, 6 years before NIST's official guidance, and said nothing publicly to explain the gap. 2026 was declared the year of quantum security by a coalition that included the FBI, NIST, and CISA, which is an unusual sentence to have to write. Think about what that sentence requires. 3 agencies whose normal operational focus involves criminal investigations, technical standards, and critical infrastructure protection have coordinated around a shared designation for a calendar year. That does not happen over a theoretical concern. That happens when agencies with access to classified threat assessments and internal timeline projections reach a common conclusion that the window for comfortable planning has closed. The year of quantum security is not a marketing campaign. It is a signal, and signals from the FBI, NIST, and CISA together are worth reading carefully. The designation came with launch events in January 2026, featuring senior officials from all 3 agencies. Not junior staff, not public affairs representatives, senior officials. The message was consistent across every appearance. The quantum threat is not a future problem requiring future attention. It is a present problem requiring present action. That framing is deliberate. Institutions at this level do not use language carelessly. When the FBI characterizes something as a present-day national security concern, that language reflects internal analysis that the public does not have full access to. Alongside the Year of Quantum Security designation, the NSA released its CNSA 2.0 framework with a specific binding deadline attached to it. All new national security systems must be quantum safe by January 2027. Not 2030, not 2035. January 2027. That is a 12-month window from the start of 2026, applied to every national security system built or procured after that date. The NSA does not set deadlines it considers aspirational. When NSA writes a date into a framework that governs national security infrastructure, that date reflects a threat assessment with classified inputs. The public version of the reasoning is available. The full version is not. The Quantum Computing Cybersecurity Preparedness Act added a legislative layer to what might otherwise remain a bureaucratic exercise. Federal agencies are now required to inventory systems that rely on vulnerable cryptographic protocols and report migration progress annually. That requirement matters because you cannot protect systems you have not identified. The inventory step sounds procedural. It is not. Government systems accumulated over decades run encryption implementations that in many cases predate the current threat understanding entirely. Identifying every vulnerable system across every federal agency is a substantial undertaking before any actual migration begins. What is worth noting about the US policy response is the continuity across administrations. Trump's June 2025 executive order explicitly preserved Biden's NSM-10 as the foundational framework for post-quantum cryptography transition. That is rare. Policy frameworks from one administration frequently get revised or discarded by the next as a matter of political differentiation. The fact that NSM-10 survived intact signals something about how the classified threat briefings read, regardless of which party is receiving them. The quantum threat is not a partisan issue. It does not adjust based on election outcomes. And apparently, The administrations that have seen the full picture have agreed on that point even when they disagreed on most others. The European response covers a wider coordination problem. An 18-nation joint statement targets 2030 for high-risk use cases to complete post-quantum migration with broader adoption across lower-risk systems by 2035. Getting 18 governments to agree on a technical timeline and sign a joint statement about it requires that the threat assessment is consistent across intelligence services operating in different countries with different dependencies and different infrastructure profiles. When the French Cybersecurity Agency and the German BSY and the UK NCSC and 15 other national security bodies arrive at the same conclusion, that convergence is its own form of evidence. The EU Cyber Resilience Act is moving toward a quantum safe by design requirement, meaning new products sold in European markets would need to incorporate post-quantum cryptography from the design stage rather than as a retrofit. Here is my position on what this institutional response actually represents. These are serious actions. The designations are real, the deadlines are binding, the legislative requirements have teeth, and none of it changes the scale of what migration actually involves. The cryptographic infrastructure of the modern internet was not built in a year. It was not built in a decade. RSA and the public key infrastructure built on top of it accumulated across 40 years of hardware, software, protocols, systems, and standards layered on top of each other across every sector of the global economy. Replacing the cryptographic foundation of that structure is the largest infrastructure change in the history of digital systems. Not one of the largest, the largest. Banking systems, government networks, critical infrastructure controls, healthcare records, communications platforms, supply chain management, every system that touches the internet touches public key cryptography, and every one of them needs to be identified, tested, and migrated to algorithms that did not exist in standardized form until August 2024. The agencies acknowledge this, the frameworks account for it, the timelines reflect an awareness of the scope. And the gap between acknowledging the scope and completing the work is exactly where the risk lives. The organizations that started their inventories in 2024 are ahead. The organizations that are beginning that process now are working against a timeline that multiple independent threat assessments suggest may be shorter than the migration requires. The organizations that have not started have a different problem entirely, and the designation of a calendar year does nothing to change their position. Declaring a year does not migrate a system. In August 2024, NIST finalized the first 3 post-quantum cryptography standards, which is the good part of this story. The standards are called MLKEM, MLDSA, and SLHDSA. Those names are not important. What is important is what they do. MLKEM handles key encapsulation, the process of establishing a shared secret between two parties who want to communicate securely. MLDSA handles digital signatures. SLH-DSA is a second signature algorithm built on different mathematics, and in March 2025, NIST added a fourth, HQC, a code-based algorithm selected specifically as a backup to the first 3. The backup matters. All 3 primary standards are built on lattice-based mathematics. If researchers discover a flaw in that mathematical foundation, every one of the primary standards fails at the same time. HQC is built on a different problem entirely. It is insurance. When you do not fully know which approach will hold, you want multiple candidate explanations standing behind the answer. That is not a sign of weakness in the standards. That is the only rational response to genuine uncertainty about which mathematical hard problem stays hard. Here is what post-quantum cryptography actually is. RSA works because multiplying 2 large prime numbers together is fast, and factoring the result back into its components is computationally prohibitive for a classical computer. Shor's algorithm eliminates that asymmetry for a quantum computer. Post-quantum cryptography replaces that mathematical problem with a different one, a problem that quantum computers are not known to be able to solve efficiently. Lattice problems involve finding the shortest vector in a high-dimensional geometric structure. The best-known quantum algorithms for lattice problems offer no significant advantage over classical computers. That is the foundation the new standards are built on. It is not proven unbreakable. Nothing in cryptography ever is, but it is the best available candidate right now, tested against every attack researchers could construct over a 6-year NIST evaluation process. So the standards exist. The question is what replacing RSA actually requires, and here is where the difficulty becomes concrete. Every system on the internet that currently uses RSA or elliptic curve cryptography has to be identified, assessed, tested with the replacement algorithms, and updated. That is not a software patch. It is an infrastructure audit followed by a migration, and the infrastructure in question is every server, every device, every application, every protocol that participates in encrypted communication. Some of those systems are updated regularly and managed by teams that know exactly what cryptographic libraries they are running. Others are embedded in hardware that has not been touched since installation, running firmware that has no update path, owned by organizations that do not have a complete inventory of their own systems. Both kinds of organization are affected by the same deadline. Cloudflare moved early. By late 2025, the majority of human-generated traffic on its network was secured with post-quantum encryption over TLS. That is a meaningful number. Cloudflare sits between a significant fraction of the internet and its users, which means their transition carries real weight. But Cloudflare is also a company whose entire business depends on being ahead of this problem. They had every reason to move fast and the technical capacity to do it. Apple integrated MLKEM into iMessage. Google has committed to a full post-quantum migration across its systems by 2029. These are the organizations that started early, that had the resources to audit their systems and the engineering capacity to implement the new standards at scale. The asymmetry between those organizations and the ones that have not started yet is significant. A company that began its cryptographic inventory in 2023 has had 2 years to identify vulnerable systems, test replacement algorithms, and work through the integration problems that always appear in practice. A company that has not yet completed that inventory is starting the same process with a shorter runway and the same number of systems to update. The migration does not get easier the longer it waits. Legacy systems become more entrenched, dependencies multiply, and the threshold problem is not symmetrical. An organization that completes 80% of its migration is not 80% protected. Every system still running RSA is fully exposed. There is another layer to this that rarely gets acknowledged directly. Replacing a cryptographic standard is not just a technical operation. It is a coordination problem. Every party in a communication needs to support the same algorithm. The transition period, where some systems support post-quantum algorithms and others do not, creates its own set of vulnerabilities. Protocol negotiation during that window can be exploited. Hybrid approaches that run classical and post-quantum algorithms simultaneously address some of this, but they are transitional, not solutions. The standards are real, the algorithms have been vetted, the replacement for RSA exists, and the engineering path to implementing it is understood. What is not uniform is who has started walking that path and how far along they are. The organizations that appear in the early adoption numbers represent a fraction of the systems that need to be migrated. The rest are somewhere in the process, or have not yet begun, running on the same mathematical assumption that the last several sections of this story have been explaining is no longer safe to make. The algorithm exists, which is not the same as the migration being done. Here is the thing that sits underneath all of this. The pattern is not new. It is not unique to quantum computing. It is the same pattern that shows up every time a threshold approaches slowly enough that the institutions responsible for responding have time to acknowledge it without urgency. The theoretical capability existed in 1994. Shor published the algorithm. The field noted it. The field continued. Then the qubit estimates arrived and gave everyone a number large enough to feel safe, 20 million physical qubits. That number did a specific kind of work. It did not make the threat go away. It made the threat legible as a future problem rather than a present one. And future problems have a particular relationship with institutional attention. They get acknowledged, they get planned for, they get a working group and a report and a set of recommendations. What they rarely get is the kind of response that treats the future as something already in motion. Here is what was actually happening while the 20 million number held. The error correction threshold that everyone said had to be crossed before the threat became real was being crossed. Google crossed it in December 2024. The theoretical assumption that underpinned every comfortable timeline turned out to be physically achievable. And then, 5 months later, the man who published the 20 million figure published a correction, under 1 million. Same problem, same algorithm, different assumptions about what the hardware could now do. 95% reduction, 6 years. That is the pattern. Not conspiracy, not negligence. Something more structural than either of those. The data was available at every stage. The 1994 algorithm was public. The qubit estimates were published and widely cited. The Willow result was announced and covered. The Gidney correction appeared in the literature. None of it was hidden. And at every stage, the institutional response was calibrated to the previous data point rather than the current one. What does that tell you about what happens next? Right now, the working estimate is 2030, 4 years. The organizations that have inventoried their systems and begun migration are running against that number. The organizations that haven't are also running against it, they just don't know it yet. And the harvest-now-decrypt-later threat means the data that needed protection was already exposed before anyone finished the sentence about migration timelines. The thing about a threshold is that it does not look like a threshold from inside it. It looks like a series of incremental developments. One paper, another paper, a hardware result, a revised estimate. Each one is notable. Each one gets covered. And the cumulative weight of all of them together, the fact that 3 independent research groups converged on the same conclusion from different directions within 12 months, that Google moved its internal deadline 6 years ahead of NIST's guidance, that the FBI and NIST and CISA declared an entire year devoted to a single security problem, the cumulative weight of all of that lands differently than any individual piece. Most of the organizations that will be affected by this already know about it in some form. The information is not restricted. The NIST standards are published. The government mandates are public. The Gidney paper is in the literature. What is not evenly distributed is the organizational capacity to respond. A large financial institution with a dedicated security team and a multi-year migration budget is in a different position than a hospital running legacy software on systems that have never been inventoried for cryptographic dependencies. Both of them are running on RSA. Only one of them knows exactly where. That asymmetry is where the actual risk lives, not in the abstract possibility of quantum computers breaking encryption. In the gap between institutions that started early and institutions that are still deciding whether to start, that gap is being written right now. Not in geological record, not in ocean sediment, but in network architecture decisions and procurement budgets and migration timelines that will determine what survives and what doesn't when the threshold on the other side of this is crossed. In 1994, the algorithm existed and the hardware did not. In 2019, the hardware was too noisy and the qubit requirement too high. In December 2024, the error correction threshold was crossed. In May 2025, the qubit requirement dropped by 95%. Each of those moments was visible in real time to anyone paying attention. The question that never gets answered cleanly is why visibility and urgency so rarely occupy the same space at the same time in the same organization. Not because the people inside those organizations are careless, because the gap between understanding a threat and restructuring around it is almost always larger than the gap between when the threat becomes legible and when it becomes consequential. The estimate changed by 95% in 6 years, and the organizations that built their planning around the old number have not yet finished updating their spreadsheets.